Okay, so hi everyone. It's my pleasure to be here today, and what we're gonna go through is an upcoming, let's say, half an hour or to 40 minutes, is a presentation about the domain-specific architectures, custom compute, heterogeneous compute, and so on. And we will also look at the tools and the automation and how this brings the benefit into the semiconductor industry and how then you can innovate and differentiate your products. If you look at the agenda, it is roughly what I mentioned. So firstly, let me kind of do the short introduction why we are looking at this problem in the first place. Then we will look at the different possible solutions, and we will zoom into the domain-specific architectures, custom compute, or these sort of things. And these architectures in general are not new because they have been here for a while. But what's new is the new approaches, how we can do them, how we can make them in a really short time, including not only the, let's say, IP block, but also other parts of the story, which means in the CPU design, also SDK and so on. And in this last part of the presentation, I will switch to the tooling and do some, hands-on exercises. And we will also have other results of other customers that we have, and finally conclude the presentation. Okay, so let's go one by one. So if you look at the semiconductor scaling problems, so what I mean by that is that after roughly 50 years of driving semiconductor economics, the standard laws that we are used to are sort of stopping or failing, if you will. So things like Amdahl's law, linear scaling, they stopped already, and they have some certain limitations. Yeah, Moore's law is sort of still in the debate whether it's stopped already or already slowing down. Nonetheless, we need to kind of look at the solutions, how we can improve the overall performance because the market demands that. So then if you look at what we can do is, the thing is that if you go to the smaller nodes, it doesn't help as much as it used to. So we need to find a new ways how we can get the performance. We should not rely on the technology nodes only. And there is also economical aspect of that because the smaller nodes are really expensive. So some changes needed, as I mentioned. We can look at the new technologies such as optics or carbon nanotubes. And don't get me wrong, these technologies are really nice. And if you are a bit familiar with those, I mean, the concepts are really awesome. But from the industry point of view, they are a bit a stretch goal at the moment. So maybe in a couple of years, 5, 10 years, we will see them more used. But in the meantime, we need to look at the different solution. And we believe that the different solution is something that we call custom compute. Some other people call it heterogeneous compute, yet another people calls it adaptive compute. But pretty much all of them kind of talks about the same thing. So let's have a system or solution where individual parts may be optimized for individual tasks, and therefore the overall performance or overall, let's say, power consumption is at the point that it needs to be. And if you look at the domain-specific architecture, particularly, we can find them that they are used or they can be used pretty much across the board, which means that you can use these small little embedded core that are highly optimized, especially with the edge computing and AI on edge. This is more and more appealing story because you do have some really nice computation on the edge, so there's no need to have a connection to the cloud, improve the security as well, and so on. So this is one of the things that we can see. Connected to this one and AI particularly, we have some specialized cores, some NPUs and these sort of things, which are also specialized for certain workloads, and they are really good at that. But if you throw another workload on them, it's not that good anymore. And therefore, we end up in the heterogeneous compute, where actually in the SoC or in the system or platform, we have a combination of those items. We have a combination of general purpose with the really optimized cores in there, and so on, which is the key to succeed in the industry. And we call it, and again, the name can be heterogeneous compute, it can be adaptive compute as well, but those are synonyms to some extent. Now, this is just really briefly why we are doing this. Besides the achieving the goal of the, let's say, target performance, you can go in this direction in several steps. So you can do it in the software level, but you can differentiate only as much as the software allows you because the underlying hardware is the same. And you can end up completely on the right side where we have, or you have, a best solution possible, which means that you have the programmable solution that is really accelerate the compute, and the energy consumption is therefore smaller, and so on. So we will, in this presentation, zoom in on this right side. We won't talk about the other part that much. We will zoom on the right side, which is about custom compute on the CPU level, on the processor level, and how we can enable anybody to do it, and how you can then differentiate and how you can innovate through the automation that is possible in the CPU design. Before we go into the detail of the solution, I like to just stop by here, and just for benefit for everybody, we will use RISC-V as a base vehicle for the customization of the CPU. Now, pretty much everybody knows RISC-V, so I won't do any huge intro. What I like to stress, though, is that one of the things that RISC-V offers is a modular instruction set architecture, which means that you can choose from standard extensions that are ratified, and those extensions can be targeted to integer, floating point, vectors, bit money, whatsoever. And on top of that, you can add non-standard extensions, which might differentiate you, might bring some security because of the nature of that. It also can you can also innovate through these custom extensions. And this is really important to stress, because RISC-V, one of the things why RISC-V is here in the first place is exactly that: is enable innovation, is enable differentiation point. And RISC-V is designed in this way, so you can add non-standard extensions into the ISA as well, while benefiting from the ecosystem that's already there through the standard extensions. And last but not least, the slide indicates of the intro. If you look how domain-specific RISC-V can look like, you can imagine this graph where on the x-axis we have the power and the area, and the y-axis the performance. Now you can start with really basic ISA configuration, and you can add the standard extensions, which are these, let's say, orange boxes. And you can go up. Usually you add instructions, therefore the power is bigger and area is bigger. On the other side, you are also the performance is going up. With the domain-specific RISC-V, what you can do is that you can actually go and you can step aside of this line, because you can add some custom instructions, can be just a few of them, can be many of them, and suddenly you may end up in a different part of the graph. And by the way, with the solution that Codasip has, you can go also you can also remove things. So the customization doesn't have to be necessarily with adding things. You can also remove things that you don't need, which might be really interesting in some low power or ultra low power designs, where you kind of strip the RISC-V to the bare minimum that you need to have in your solution. As I mentioned in the introduction, the idea of custom compute or domain-specific compute is not new. It's been here for a while, but the approach that used to be taken is a bit different than what we promote as of today. In the, as I call it, all manual way, what you need to do is that if you would like to go to the custom compute world or domain-specific world, then in the CPU world particularly, you need to have a compilers, which means, for instance, GCC or LLVM. So you need to have a guys or team that knows what to do, that knows how to customize the GCC. So then the instructions are leveraged to the maximum. That is yet another task that you need to do, because you need to have the instruction set simulator and profiler that helps you with the process of customization, to finding out whether instructions are right, and so on. So you have yet another team there. Then, of course, you have the RTL, so you need to implement that in the end of the day. And connected to that, you need to have the verification team that kind of looks at that and verify the solution in the end of the day. I mean, in general, there is nothing wrong with this approach, and we can see that approach taken even nowadays. But what if you can automate some of it, if not all of it? Which is exactly our vision in the Codasip. We would like to automate this process as much as we can. And we do it through our Codasip Studio that you can see on the right side, where the input to the Codasip Studio is a processor design written in the architecture description language, which we call CodAL. So this is the input to the Studio. And the Studio then generates all the things that I just mentioned. So it generates a compiler. The compiler is aware of new instructions. You have the instruction set simulator, debuggers, profilers. These are, of course, aware of new instructions. And then you have an RTL and test bench and some other verification tools that you can integrate into the verification strategy that you have inside your own company. Which means that we kind of automated the flow. And if you need to do change, if you need to do some exploration, you do just change one thing, one single source of the truth, as we call it, and the rest is then done for you automatically. And in the remaining part of the presentation, we're going to zoom in into this process. This process takes as an input the processor model in the CodAL language. Now, you can design this CPU from scratch, but we believe that there is a better way how to do it. And it is that you can use one of the RISC-V processors that we already have inside of the portfolio. Now, these processors, RISC-V processors that we have, there is a wide range of them. We can start with the embedded CPUs up to the multi-core cluster in the application class CPU. The point being here is that all of them are written in CodAL, so which means that they are indeed an input to the Studio, including the application class CPU in the multi-core cluster. And they are designed to be customizable, which means that you don't have to spend the time doing or inventing the wheel, which is the standard RISC-V. I mean, you can if you want to, but you can start with something that is already there. And those are not an examples. Those are fully verified RISC-V CPUs, which you can take as is, if for whatever reason you don't want to do customization, but it allows you to do it if you want to. So the combination of those two are actually key, and this is why we are disturbing the market in the RISC-V, because we allow people to differentiate, and we give them the starting point, and they don't have to reinvent the wheel in the first place. And the starting point is not an example, it's not a template, it's a full-blown, fully verified CPU that you can take as is. So how does it work in more detail? So we will go kind of, a level below and below. We just introduced, okay, we have the CPU design in CodAL, we have a tooling. So how the tooling actually works? Well, the tooling works in a way that, again, the RISC-V CPU is an input. It can be your own design, it can be our design, and in fact, it doesn't have to be RISC-V in the first place. It can be your customized size as well if you need to. So if you have some kind of legacy design or some bright, really crazy idea, then you can do it as well. Then the Studio generates a bunch of outputs. More precisely, we talk usually about the SDK and the HDK. We talk about the software development kit and the hardware development kit. And I will zoom into the detail in the next slide. So these are the outputs. And what the Studio does besides that is that it can also take the source code that you would like to run on the CPU. And the source code then can be profiled. And the Studio, through the profiler, gives you some idea on maybe instruction fusion. Maybe it gives you some idea where the hotspots are. It gives you some information about how the execution actually was done. And based on that, based on these hints, then you can close the loop and you can go back to the CodAL description, change, maybe add instructions, change something in there, click on the button, get the new SDK, get the new HDK, and check that the result is indeed what you want. So this loop is essential because then you have the compiler in the loop and you have the RTL in the loop, which allows you to do really nice and a lot of iterations, even within the day. And now I know what I'm talking about because we are active a member of the RISC-V community, and we are proposing some ideas on the instruction set. And many of them are done through the studio profiling and studio exploration because it allows us to do many of them in parallel and within a day. So if you zoom in into the HDK and SDK, so the HDK consists of the RTL, well, the implementation of the CPU. Currently, we use System Verilog. It has also a test bench, which kind of allows you to do some integration, simple checking that the top level verification or top level test bench is working correctly. We provide some EDA scripts so you can do the synthesis and so on. And we have the UVM environment that's generated from the CPU description as well, that you can take and you can use as is, but the expectation is that you will build on top of that and you will make it much better solution in the end. Now the UVM can be top level, it can be also a unit level, that depends on your requirements. On the SDK side, we are LLVM house. So we produce the LLVM C/C++ compiler, but not only compiler, we also have the assembler, debugger, disassembler. Everything is LLVM based in this case. So for instance, as a debugger, as a front end, we use LLDB. We also use the OpenOCD and other tools for the on-chip debugging, something that you would kind of expect. Speaking of the on-chip debugging, you can use also other RISC-V vendors such as IR or Lauterbach or Seger. It works out of the box. You have access to the simulators and actually different flavors of them. So you can use a standard load instruction accurate or standard ISS. You can also have a cycle accurate simulator, which is faster than the RTL simulator. So it brings a benefit into the game. Or you can use a co-simulation, which means that if we have some sort of system on chip in the system C, we can easily plug our CPU, our generated CPU there. And the generated CPU, of course, has the new instructions in them. And we can leverage the whole solution or virtual platform. Or we can use this for the verification purposes as well. Now, it's all nice. We have the outputs. So let's focus on the input. So I mentioned that all of the CPUs are written in the architecture description language, which we call CodAL. CodAL is like a C syntax-like language, if you will. And it's really easy to learn, I believe. It's really easy to follow. And if you look inside of the language, among the other things, we can kind of say that certain constructs belong to the automation, certain constructs belong to abstraction, and certain constructs are sort of essentials. So we will go one by one. Basically, what it means that some of the constructs are really high level, and you just give a guideline to the tooling how to generate the RTL. So speaking of the automation, for instance, you don't describe decoders or you don't describe the pipeline explicitly. Those are inferred from the description. So you just describe, okay, I have a 5-stage design and I have a certain units over here, over there, and the tooling will infer the registers automatically and the pipeline controller automatically for you. Or the same goes with the decoder, for instance. So you just describe the encoding is like this and the decoder is then inferred automatically. So that belongs to the automation. Then we have the abstraction. And we can imagine that instead of writing, I don't know, 100 lines of system Verilog, you just write 10 or you just write 5. Because we have the abstraction layers and that kind of reduce the code that you need to write. So the way how the resources are handled, things like registers or register files that are really easy to write, or the things like the bus interfaces are really reduced to a single line in some cases. Or things like templating. So you would like to have a templated classes that belongs to the abstraction as well. And finally, we have the essentials. And essentials means that you have all sorts of the operations or operators that you are used to, but not only in the C language, but also in the other languages like Python, System Verilog, and others. So we brought together the operators that are really useful, like repetition from System Verilog or concatenation, again from System Verilog, or the way how we can call functions with innate arguments. This is taken from Python, for instance. So we are trying to kind of combine all the good things that we can see in the industry in the code in the end of the day. So zooming into each individual items a bit more. So essentials, as I mentioned, we borrowed a few things from the different languages. We have explicit bit types in the CodAL. So you have the unsigned integer on, I don't know, 13 bits or 7 bits, fully supported. We have concatenation, repetition, extraction, pretty much everything that you are used to, usually from the HDL languages. We have essentials for wires, registers, interfaces, and so on. And you might also think or use some specialized blocks that we have. These blocks are basically created from other essentials in the CodAL, but then you can just use it as a marketplace, if you will. So you can just take, okay, I'm interested in the on-chip debugger, please give it to me. So, and the tool will just give it to you a RISC-V on-chip debugger according to certain configuration. Abstraction, this is what I mentioned. So on average, we can see that we have 3x smaller code size. This is just an example of the register file. So in the CodAL, we focus on the declarative way how the register file is written. So you basically says how many ports you have, size, reset values, and so on. You can have more, of course, than that. And this is it. And then you can just call register file GPR, read or write, and that's it. And the tool will do automatically everything for you. While in the case of the system Verilog, of course, we can write it, but it's a bit longer. Now we can argue that this is not exactly the way how you would write the register file, and I would say, oh, that's okay. But this is just an example that we took from some GitHub repository that implements some RISC-V solution. So this is what we found on the internet. It obviously is not the only way how we can write it, but this is a representative example or code snippet, and you can see the reduction already there. Last but not least is the automation, which brings the most benefit into the game because it simplifies design even more. So it's not about the abstraction, it's about the automation. So if in this example, if you look at the decoder, so the only thing that you need to write for the decoder is the binary section of the element that describes instruction. The binary is then, among the other things, an input to the decoder generator. And then in the end of the day, you have a very nice block either in the RTL or in the simulator that encodes or decodes instructions. The same line, by the way, is then taken for the SDK. So the same line is then taken by the SDK generator. So then the compiler knows how to encode instructions, assembler, the linker, and this sort of things knows that as well. So single source of the truth. And then through the automation, different tools will leverage this information. Another example would be the auto pipelining that I mentioned. So the way how the pipeline is sort of created automatically for you. And we will see example in the demo how it's done. And there are more than that. So we have automation for on-chip debugger as well. Even though the on-chip debugger can be seen as a block written using essentials, but there's another set of automation rules that we have on top of that brings everything together. And you as a user sort of kind of done under the hood, and you can just see the debug in the end of the day. So this is part about the tooling. Now I mentioned that actually the story has 2 points. Tooling is one, RISC-V CPUs is the second one. I briefly mentioned that. So we have the embedded class CPUs, and we got some really good prices. You can see that we won the prize in the Embedded World 2022 with the L31. We have also application class CPUs running Linux in the multi-core cluster, all of them designed in CodAL, all of them designed for differentiation. We also have some security add-ons. And this year we won the award in the Embedded World again, but in the different field, in the field of the security. So we have a solution that implements Cherry technology, which is security framework. And with any other core that you can imagine, we have the FPGA platforms that we can use for fast bring up of a solution and testing and benchmarking or whatever. So this is also important to realize that this is part of the game. And one thing that I like to stress one more time is that those CPUs are designed for the differentiation, so you can customize them. They are designed in this way. And if you are worried about the verification, depending on the level of changes, it can be a real piece of cake because we provide you the so-called bound customization framework, which means that if you do customization in a certain sandbox, the verification is done for you in advance. In other words, you cannot break the core even if you try, because whatever you put in the bounded customization block, it will not break the core, and we guarantee that, which is really helpful for the guys who are a bit afraid of the verification. So then with this approach, the fear is gone because they can focus only on the part that they did. They have to verify that part, of course, but they don't have to verify the CPU itself because that's already done by us, and it's proven that you don't break it. This is just a zoom in into one of the embedded CPUs, and you can imagine that the CPU has pretty much everything that you can expect. Debug, interrupt, different instruction set, extensions, branch predictions, and so on. And more importantly, this white box over here that enables you to do customization. So this is just an example of one of the embedded cores, nothing really important, just wanted to showcase that it has everything in it. We don't do compromises on the PPA, even though it's customizable. So these are fully functional cores, fully verified cores. And last but not least, before the real demo, we have this FPGA platform. So this is just an example of Genesis 2 board. You can kind of use a bitstream that we already generated, upload it to the FPGA, connect to the debugger, upload the application, and you are free to go. This applies to the embedded as well as application class CPUs too. So you can put Linux there quite nicely. And it comes with a bunch of examples. So the main reason for this one is to kind of have a reference design to get up and started very quickly. That comes with the IPs as well. Now, let's finish the theory and let's dive into the demo. So I will stop share this screen. I will start sharing a different one. So bear with me. Okay, hopefully you can see the studio. As you can guess, this is a IDE that's based on the VS Code. So we are just contributing with certain plugins into the final solution. And what you can see on the left side is my workspace. And we have a couple of different folders here, and two of them implement RISC-V CPUs. I have one that I called RISC-V Vanilla, which is the non-modified CPU. And then we have the one that we will modify and we will kind of customize for the certain workloads. On the right side, we can see different targets we would like to, or we can do with the CPU. We can generate the RTL over here, we can generate the SDK, you can do some testing and so on. So this gives you targets or tasks that you can do with the project, with the CPU project. The rest of the projects we can see, like bit count or bit reverse, those are software projects, and we will use them in the demo to kind of verify what's happening and how we can maybe find out whether the new instructions were used automatically, or we can then run some sort of profiling to find out whether the new instructions helped, and if so, how much. Before we do to the customization, let me really briefly describe what you can see inside of the CPU project. Probably the most important part is the module. The module is the code source in which we capture the instruction set, microarchitecture details, and so on. So let me look at the instruction set definition first. So if I go to the RISC-V I instructions, which is over here, then let me just really briefly describe what you can see here. We have the element, and basically the element describes the instruction or instructions in this case. We have in this case the I type, which means that we have the register immediate instructions. we have a certain opcodes connected to these elements, and the opcodes are written over here, and those opcodes are taken from the RISC-V spec, as you can guess. So we have the ADDI and so on. We use two register operands, one as the input, second one as the output, and then we use the immediate that hold the immediate value, of course. We have two sections that are important. One is that defines how the instruction looks like in the text. So we have the opcode, and again, the opcode is text you can see over here. Then we have a destination register, comma, source one, comma, and the immediate. Now the immediate is a number in different, radixes. It's up to you as a coder or software developer. And then we have a binary section that defines how the instruction is encoded. And now this follows, of course, RISC-V spec. So it follows whatever the I format is about. And then, more importantly, we have the semantics section that defines the behavior of these instructions. And we can see that we have a stage annotations over here as well. So we can see that, okay, this logic is done in the ID stage, that logic in the execution stage, and finally in the writeback stage. The important thing here is that thanks to these annotations, thanks to the information that I have over here, I can infer the pipeline, or we can infer a pipeline. So we can do then the fact, we know then that the registers are read in the ID stage, the immediate is taken from the decoder in the ID stage. Then we pass the data to the LLU module that does the computation in the end of the day, and returns the data back to the variable D. Then it's passed to the writeback stage and finally written back to the register file. It is as simple as that. No magic in the coding. So this is the reason why I mentioned that I believe that it's easy to follow. If you would like to do another instruction, say register to register, which is over here, it's somehow similar. So we have again the element that describes this class of instructions. It is the R type in this case. We have the assembly section. In this case, we have 3 registers, as you can see. We read 2 registers in this case, and we pass to the LLU, and then do the result, taking the result back. And pretty much every single instruction is written like this. So there's really similarity in this case. And for instance, the low store is written in a similar way, or the branches branches and calls are written in a similar way. So now we have this instruction set definition written. We have the modules that we saw over here, like LLU, and these modules basically implements whatever you as a designer decides to do. So in this case, it's a single cycle LLU. And as you can see over here, we use the abstractions. So this LLU actually can be used in multiple CPUs because we give it the word bit as a templated argument, and then it's propagated to the logic itself. You can have far more complicated units, of course, that deals with much more complicated computational stuff. But this is an example how the modules are done in general. So we have the ISA, we have individual modules that kind of do the real thing, do the computation, and then you can have some other resources definition, like which registers you're gonna have over here, like. This is example of the register file, for instance, where we can see that we have only 2 reading ports, 1 writing port, and so on. So we define this information on the CPU as well. So we have this description of the CPU. Cool. We can generate the SDK now. For the sake of time, I already did it. So I pre-built the SDK for the vanilla. And what I can do right now is I can start compiling the CPUs, the software projects. So if I build the bit count, I can build the project over here, it's built. What I can do right now is I can start debugging as I'm used to. So this is just a vanilla RISC-V. I have some sort of benchmark over here. I can start debugging. And as you can see, I have all the capabilities that I need for the software debugging. I can jump through the code. I can see the values of the register of the variables. I can even see the values of the registers or even the microarchitecture registers. So I have a full visibility into the into the software project. So the debugging is very important, and of course it's fully supported, even on the custom instructions. So I wanted to just showcase that for the software developers, you can enjoy the fact that you can use a standard approach that you are used to, and everything is fine. But more fun is with the customization, right? So I have two examples of that. So I have a simple Mac operation, and the purpose of this demo is to kind of show that I have this C code written like this. I have a function that implements the Mac, and I have written it in the C. In this case, it's quite kind of straightforward C because I have multiple two values, and then I have some sort of benchmarking main. And the goal of this exercise is to create an instruction and let the compiler recognize this instruction in the C code. So let's go into the customized RISC-V. And what I did over here is that I've created a Mac operation. Now the Mac operation is interesting for one reason, and that's because you need to add one more reading port. Because for the Mac, you need to read 3 sources, which, as you can see, as easy as this. So the only thing that I did in the customization through the abstraction layers is that I've added one more reading port over here. In the original code, I had only 2. In this code, I have 3. And I'm reading 3 operands, and I'm reusing the address of the destination registers as one of the source to save some coding of codes. And I've created the Mac unit that does the multiply and accumulate. And for this example, I'm not interested in the sharing of the multiplier, even though I can implement it in this way. But for the sake of simplicity, let's do it independently. After the Mac is done, I can write the result back. Now, if I look at how the Mac actually looks like, which is in my module, which is over here, it's quite simple. I indeed do just multiply and accumulate. And that's pretty much what I need to do. I can share the multiplier with already existing multiplication unit if I want, but for the teaching purposes, I decided not to do it, and let's have it like this. So now what I can do is I can try to compile the Mac, because I pre-generated the SDK already to save some time, so I have the vanilla one as well as the new one. So if I go to the Mac, then I can compile it using it no extension. And if I do it and I go to the no extension, and if I look at the assembly code, what I will find out that there is indeed multiple and add instructions. So if there is no extension, the compiler will use what is kind of obvious, which is multiple instruction and accumulate instruction. Now what I can do, because I have the extended SDK, I can compile it using the extended version of that. And in this case, if I do it and go to release, and if I open over here, I can see that the compiler used the Mac instruction fully automatically. I haven't changed the C code whatsoever. I just changed the SDK, which is quite a powerful statement, because then if you need to just recompile your code, it's quite powerful. And you can say, okay, the Mac is quite simple. Well, yes, that's true. Can be much more hidden. You can use the memory accesses as well, but in the end of the day, the pattern is somehow simpler. So let's look at a more complex example, which is the bit reverse, which I have over here. So if I go to bit reverse, I can see that it can be written in many ways. It can be written in some sort of naive form with the for loops. You can also implement this using some bit manip operations. So let's look what we can do in this case. So let's go to the model again, and let's try to look at how the bit reverse can be implemented. And again, the same story. I have my extension definition of my instruction. So I have my bit reverse instruction over here. It has only one input and one output, which is simpler. And which means that I can just read one value. I'm going to compute the result, and I'm going to store it back. So kind of similar to the previous one. And if you look at the implementation of bit reverse, in this case, I can do it in the for loops as well, But in this case, what I like to show you is that you can also enjoy the fact that the CodAL comes with the pre-built functions or operators that are quite common in the RTL world or in the processor world. And in this case, the bit reverse is already prepared for you as a designer, so you don't have to kind of reinvent the wheel. You can just instantiate the function and call the function, and that's pretty much it. Now, if I do it, then what's happening is that I can again showcase two builds. One that's built without extensions. And so you can see that without extensions, the bit reverse is using the standard bit manip instructions, as you can guess, because this is how it's written. But if you look at the improved version of the bit reverse, we can see that the compile again used the instructions automatically, even though the code is far complex, right? You have loops, you have different bits operations, but yet the new instruction has been taken into account and it was used automatically. Now, to kind of verify that in the runtime, we can run the profiling, and if I run the profiling without extension, then what I can find is that without extension, it took about 12,000 more than 12,000 cycles. And if you look at the annotations, if you look at the where the time is spent, then we will see that the most of the time is of course spent in the code. So if I run the profiling again with the new instruction, then we can see significant speed up, because suddenly we have a less than 5,000 cycle, which is really a big improvement just with a single instruction. And you can, of course, as I mentioned, use the information that you can find in the profiling for the instruction fusion, for the source code coverage. So you can kind of see where the time is spent. So with the new instruction, the majority of the time is spent actually in the main, because the bit reverse is quite optimized. If I go back and if I showcase the original start, we can see that if I go to the source code annotation, then the most of the time is spent in the bit reverse rather than the main, which is kind of expected, right? Last bit I like to show you is then the RTL, because the RTL is an important part of the story. And our RTL, we pay attention quite a bit. So the RTL is actually readable. So if I open the implementation of our new instructions in the RTL, thus you can see that we keep IDs as much as we can. We use the modern style of the writing, so you can see the mark instruction over here. And by the way, this is the bit reverse instruction, and you can see that because it's already implemented in the best way possible, it's not kind of translated to function call one-to-one. We actually translate that to something that is done quite efficiently in the RTL as well. So we can then enjoy the fact that CodAL has some additional operators that does it for you fully automatically, and you don't have to kind of pay attention to low-level details. You can focus only on things that matters to you. I'm going to switch back to presentation. Which leads to a couple of more examples with the customer names on them. So for instance, we did work with Microsemi. Thanks to the custom instructions, and in their case about, I think, 30 or 40 instructions, we increased the performance by more than 50x, which is quite significant, even though the area has increased 2.5x almost. But then if you compare the gain that you get from the custom compute is really helpful. Another example is then a Mythic. They did AI solution for the inference and these sort of things, and we were part of their design. Our CPU were there again customized for their needs. It was designed in 2 months because we could start with something that was already there. We started with the L31 in that case. Because of that, the development time was quite reduced. And we are also doing edge AI solutions. So this is just an example of number recognition. And we were able to reduce the time by 80% by few instructions. And the energy consumption was reduced as well, almost 80% as well. And no additional cost means that we did really smart instructions in this case that cost almost nothing in this case. So to conclude this presentation, given to the fact that semiconductor is struggling with the scaling needs and with the law that are slowly but steadily creating problems, we need to look for the new solutions. And in our from our point of view, the new solution in a given time frame is a heterogeneous compute. With the heterogeneous compute, you need to have sort of way how you can automate customization, how you can automate the domain-specific accelerators, and combination of the RISC-V as a baseline and the tooling, in this case, Codasip Studio, is really key enabler for these activities because you don't have to reinvent the wheel. You can build on some really good foundation, and not only on the RTL level, but also on the SDK ecosystem, on the software ecosystem. And then with the automation that Codasip Studio in this case provides, then the customization is actually not a problem, not a big deal, because as you saw in example, it was roughly, I don't know, 50 lines of code, and you saw immediately an action or improvement in the case of the benchmarking. And you can imagine that you can do much more than that because of the fact that the automation gives you the SDK and HDK automatically and verification tools, of course, at the end of the day as well. Which leads to the end of my talk today. I'd like to thank you for your attention, and I'm open to questions.
Thanks a lot.